Greetings, Eclipse Pioneers. It's Steve at the Planetarium, and it's eclipse seasons. And you may remember we made our eclipse timelines in our class, and we noticed that eclipses seem to be bunched together at certain times of year and wondered why that happens. So let's find out about that. Here's the ecliptic. You've seen it in the dome, in the planetarium sky, the orange dotted line in the planetarium sky, showing where the sun is compared to the stars in the background for every day of the year, as it appears from our point of view here on Earth. And let's say it's August 1st. So the sun is at August 1st on the ecliptic. Now let's add the moon. This line is the moon's orbit. And you remember the orbit of the moon is tilted about 5 degrees compared to the ecliptic. The place where the moon's orbit crosses the ecliptic is called a node. This one would be the ascending node because the moon moves this way, so it's going from below the ecliptic to above the ecliptic. That's ascending. On the other side of the sky, where we are not looking right now, there is a descending node. Let's say at this particular moment, it just so happens that the node is right at the August 1st position on the ecliptic, and at that moment the moon is at the node. From your point of view, then you are very fortunate. You are in exactly the right place at the right time to see a total eclipse of the sun, the moon perfectly blocking the sun's disk. But what about your friends up in northern Canada? Up in northern Canada, they are a little above the moon compared to you. So from up in northern Canada, the moon appears a little bit lower, and your friends up there are seeing a partial eclipse with a bite taken out of the bottom of the sun's disk. And what about your friends in southern South America? Well, compared to you, they are a little below the moon, so they see the moon a little higher than you do, and from their point of view in southern South America, they are seeing a partial eclipse with a bite taken out of the top of the sun's disk. This is interesting because if we want to be able to predict eclipses well enough to tell when at least a partial eclipse might be visible from some place in the world, then we have some leeway. The sun could be as far over as, say, about July 14th or so, and even if the node is here, if a new moon occurs near that July 14th date, or on that July 14th date, and new moon is technically the moment when the moon crosses an imaginary line through the sun that's perpendicular to the ecliptic, that new moon is close enough that somebody somewhere on planet Earth would have a chance to see at least a partial solar eclipse. And even if the sun is way over here, say about August 15th or so, a bit away from the node, but if a new moon happens to occur at that place around August 15th, 14th or 15th, that's close enough that somebody somewhere on planet Earth would have a chance to see at least a partial eclipse of the sun. So there's a range of dates on either side of the node when some eclipse is possible. That's called an eclipse season, and on average an eclipse season is about 35 days long. There are 2 eclipse seasons, one for the ascending node and one for the descending node. Every eclipse season must contain at least one solar eclipse. To see why, remember that the moon revolves from new moon to the next new moon in about 29.5 days. So a lunar month from new moon to new moon is shorter than the length of time of an eclipse season. So at least one new moon must occur during each eclipse season. That means there must be at least one solar eclipse in each eclipse season. Because if a new moon happens during an eclipse season, there must be an eclipse. And if a new moon occurs near the beginning of an eclipse season, there's time for the next new moon to occur near the end of the same eclipse season. So sometimes we can have 2 solar eclipses only 29.5 days apart. They'll probably be very different eclipses and visible from different parts of the Earth, but 2 eclipses nonetheless. Now, the nodes are points on the ecliptic. If the nodes did not move, then the sun would cross each node once a year on the same date each year, 6 months apart. But the nodes do move very slowly in the opposite direction from the apparent motion of the sun. That's called regression of the nodes. The nodes take about 18.6 years to regress all the way around the ecliptic. So the sun will return to this particular node in a little less than a year, about 346.6 days. And the sun will go from ascending node to the descending node in a little less than 6 months, about 173.3 days. That means each year will contain at least 2 eclipse seasons and possibly part of a third. Here's our eclipse timeline. And here's a ruler I made in which I made marks one node crossing apart. These are about 173 days apart, and I shaded in the eclipse seasons. So we can look at what happened in, say, 1901. It appears that there were 2 eclipse seasons in 1901 and 1 solar eclipse in each one of them. But it could be different. Let's take an imaginary year here. You could have 1 eclipse season beginning right after New Year's Day or right on New Year's Day, and then you would have time for a full eclipse season at the beginning of the year, another full eclipse season in the middle of the year, and a bit of a third eclipse season at the end of a year. Each eclipse season must have at least 1 solar eclipse and can sometimes have 2. So a year could have as few as 2 solar eclipses, say 1 in this eclipse season, 1 in this eclipse season, or as many as 5 if we have a situation like this. 2 eclipses in this season, 2 eclipses in this season, and another eclipse in this third season. So in any calendar year, the number of solar eclipses can range from 2 to 5.